Here's a screencast on Unit 2 for AP Chemistry, Chemical Bonding, and we're going to cover just some of the topics under Topic 2A, States of Matter and Solutions. So Topic 1A, Atoms and Elements. States of Matters. These are the things that we will cover. We won't cover all of them today. So Topic 1A, Atoms and Elements, has states of matters, gases, and kinetic molecular theory, sometimes called KMT. And so we'll look at KMT, gas laws, ideal gas law, Dalton's law of partial pressures, deviations from the ideal gas law, root mean square, Graham's law, and Henry's law. And then in solutions, we'll look at chromatography, distillation, and dilutions. So topic 2A, states of matter and solutions. States of matter. All matter has two distinct characteristics. It has mass and it occupies space. The properties associated with the three states of matter and the behaviors of the particles that make them up are summarized below. So there are solids. They have definite shape and definite volume. The particles are packed tightly together and only vibrate gently around fixed positions. So here's what a solid looks like. The liquids. They have no distinct shape. They take the shape of their container. They have definite volume, and the particles are free to move around. Gases, neither definite shape nor volume. Particles spread apart, filling all the space in the container available to them. So there's no definite shape or volume because gases are compressible. Those empty spaces between them, you can compress them. Solids fall broadly into two categories. Crystalline, where a regular, ordered, repeatable 3D structure of particles is found, or amorphous. A means without, and morph means shape, without shape, where the arrangement of particles is not regular or ordered. However, in both cases, the particles in the solid have very little energy and move very little in relation to the other parts. I'm missing a word in there, huh? Liquids. Like solids, liquids have particles that are very close together, but unlike solids, the particles in liquids are constantly moving and colliding with one another. They have significantly greater energy and move a lot in relation to one another. Since solids and liquids tend to have their particles very close together, their volumes are often very similar. Since in a gas, the particles possess enough energy to overcome any intermolecular forces, that's the forces between the individual molecules, and hence move around completely freely and with large spaces between them, a liquid represents particles in an intermediate state between the extremely ordered and low energy state of a solid and the extremely disordered and high energy state of a gas. The properties of solids and liquids. All of the properties of solids and liquids, such as viscosity, surface tension, hardness, etc., are dependent upon how the particles that make up the solid or the liquid are arranged, and the extent of the attractions between those particles. For example, a liquid where the particles are attracted to one another with very strong interparticular forces is likely to become more viscous than one where the force of attraction is weaker. Now, viscous is a little bit like water versus syrup. Water is less viscous, meaning if you were to pour it down a ramp, it doesn't go quite as fast as something that's viscous like syrup. Heating and cooling curves. Since the different states of matter have particles with differing energies, converting between them requires a change in energy. The changes in energy associated with phase changes can be quantified in heating and cooling curves, or when heating and cooling. Gases and KMT, or kinetic molecular theory. Gases are made up of particles that have relatively large amounts of energy. A gas has no definite shape or volume and will expand to fill as much space as possible. As a result of the large amount of empty space in a volume of gas, gases are easily compressed. Pressure. A pressure is exerted when the gas particles collide with the walls of any container it is held in. Pressure can be measured in a number of units, for example, atmospheres, millimeters of mercury, torr. So more about KMT. The kinetic molecular theory is the basis for many properties of gases. The 5 postulates are: gases are composed of tiny particles, atoms or molecules, whose size is negligible compared to the average distance between them. This means that the volume of the actual individual particles in a gas can be assumed to be negligible compared to the volume of the container, and therefore the total volume that the gas fills is almost all empty space. The observation that gases are compressible agrees with the assumption that the actual gas particles have a small volume compared to the total volume, example, the volume of the container. 2. The gas particles move randomly in straight lines in all directions and at various speeds. 3. The forces of attraction or repulsion between two gas particles are negligible except when they collide. 4. When particles collide with one another, the collisions are elastic. No kinetic energy is lost. The collisions with the walls of the container create the gas pressure. Elastic collisions agree with the observation that gases, when left alone in a container, do not seem to lose energy and do not spontaneously convert to the liquid state. 5. The average kinetic energy of a molecule is proportional to the Kelvin temperature, and as a result, all calculations involving gases should be carried out with temperatures converted to K, or Kelvin. So using Kelvin eliminates the problem of negative temperatures leading to negative energies and negative volumes, etc. These real assumptions do have limitations. For example, gases can be liquefied if cooled enough. This means real gas particles do attract one another to some extent. Otherwise, the particles would never stick to one another and therefore never condense to form a liquid. Gas laws. So we covered the gas laws in first-year chemistry: Boyle's, Charles, Avogadro's, Gay-Lussac, and the ideal gas law. Ultimately, all you need to know is PV equals nRT. You can get all the other equations from that one. And this is what it essentially looks like in the proper form, which I didn't show this proper form to you last year. So P1 V1 N1 T1 equals P2 V2 N2 T2. You just have to make sure you have your 1s in the proper place and your 2s in the proper place. And even if you're not using one of those variables, for example, if you don't have moles, you just don't use it in there. So pressure and volume have an inverse relationship. It's a negatively sloped line. So if one increases, it means the other decreases. Pressure and temperature have a direct relationship. So if pressure increases, it means the temperature is increasing. And it's a positively sloped line. One to note, Avogadro's law. At constant temperature and pressure, volume is directly proportional to the number of moles of gas present. The volume of a gas increases with increasing numbers of moles and vice versa. So these are helpful ones that we talked about a little bit in first-year chemistry. So pressure times volume equals mass times R, the universal gas constant, times T, temperature has to be in Kelvin, divided by mm, which I call molar mass. So the masses you add up from the periodic table. I like to rearrange it, and if you remember this one, it probably will get you almost anywhere. So molar mass equals density times R times T divided by P. And the way I remember this is molar mass equals dirty P. I never forget it, because is P ever dirty? Probably not. So R is 0.0821 liters, atmospheres, inverse moles, inverse kelvins. I'm skipping a huge bunch here, going to partial pressures. The total pressure of a container, perhaps with different gases in it, is the pressure of the first gas, plus the pressure of the second gas, plus the pressure of the third gas, etc., however many gases there are. So that pressure total is the moles total times R times T divided by V. A mole fraction equals the moles of a gas, perhaps gas A, divided by the total moles of gas. So whatever gas you're looking at divided by the total moles of gas. And so all the mole fractions for all the gases should add up to 1. Partial pressure of a gas is directly proportional to the number of moles of gas present. So the partial pressure of A is equal to the total pressure times the mole fraction. A mole fraction is, I guess I didn't put that funny X in there. X stands for the mole fraction. So Boyle's law. We have pressure and volume. So if the pressure, I'm trying to read this graph, it's inversely related. So if the pressure decreases, the volume increases. So it's like if you had a syringe and you let go of the pressure on it, the volume inside would increase. It means that you're not squishing the molecules as close together. Charles' law is a direct relationship, so if temperature increases, the molecules are moving faster, they're occupying more space, there's more space between the molecules, and hence the volume increases. Charles' law is volume and temperature, and this is Charles' law with temperature in Kelvin. That's the one with Celsius, so it's the same thing. Same relationship, just different type of temperature. Dalton's law of partial pressures. Dalton's law states that in a mixture of ideal gases, the total pressure exerted by the mixture is equal to the sum of the individual partial pressures of each gas. So I think we already talked about this. The pressure total is P1, P2, plus P3, etc. And if you would assume ideal gas behavior, you could simplify to this. The total pressure is the moles total times RT over V. And those are the end of our notes for just the first section in topic 2A.